So with that, we can start recording. So again, apart from the announcements I've already made, I've given you some guidance in your class notes here as to what to focus on in these chapters. I do the same thing in chapter 31, which is on polymers. Of course, chapter 30, we're not covering. You'll never be responsible for it. It will not be on the final exam. But these two chapters do have a somewhat different format or focus, and I want to make sure that I'm clear on what we're focusing on and what you should be focusing on. I'll also just mention that I've been pretty here, scrolling down, I've been pretty clear in the class notes on what you will and will not have to know. So I've tried to spell that out as explicitly as I possibly can. Though I want to treat you guys like the adults that you are, at the same time, I don't want you guys guessing about things like that. So, since we've already made the point that the reactions that occur in biochemical pathways, in the cell, if you will, are the very same reactions that we've learned throughout this entire year of organic chemistry. And so what we've learned in organic chemistry is directly relevant to things that you're going to have to know later on in order to get into medical school, and certainly in those exams. Admittedly, the focus is somewhat different. Organic chemists are rather obsessed with structure. I think you've noticed that by now. We certainly like to discuss mechanism whenever we can. And I'm, at least in certain ways, gratified that in biochemistry, they're becoming more and more interested in mechanism with each passing year. That's the good news. The bad news is that can get extremely complicated when you start bringing enzymes into the picture. So in that sense, I'm certainly not going to expect you guys to learn any enzyme mechanisms. And I say this in the class notes. I don't want you to reinvent the wheel at this point. But my focus is, and I hope your focus as well, will be on how can we understand these pathways as examples of reactions we've already learned and organize them using the same principle. And in so doing, can we just look at these biochemical pathways as just examples of things we've already learned for this class? So that's what my goal is going to be for us. And I think if you give me a chance, if you'll just keep an open mind to all this, I think you'll see that it works pretty well. Good. So today, what I really want to cover, since we're not going to do every single biochemical pathway in the chapter, and I've listed out what are the ones that you should focus on in the class notes, but I figured a good place to begin is the same place your textbook began with all this. In chapter 29, I think it made an excellent choice, which is biochemical energy. In order to have life in any conceivable form, we have to have energy, and we have to have a way of getting energy to run our biochemical pathways. And there's multiple ways that this is done, but one of the main ways is by hydrolysis of ATP and related molecules. And so this is, I think, something that you'll have learned in your biology classes already, but I just wanted to point out that this idea of hydrolyzing ATP to get inorganic phosphate and ADP is not just some weird special thing that only occurs here and has no relationship to anything else, some weird thing that is a one-off deal that we couldn't possibly have known that this is going to be what produces energy. No, exactly the opposite is true, and I hope to convince you guys of that. But over here, I've shown at least the most part, at least the business end of an ATP molecule. I'm abbreviating the entire adenosine portion over here. That's not going to change during the course of the reaction. But what happens in hydrolysis of ATP is we're going to break one of these phosphorus-oxygen bonds. And I bet in your biology, as well as in your eventual biochem textbook, they're going to call these phosphorus-oxygen bonds high-energy bonds. And I bet they wrote little squiggly lines there, even in your biology textbooks, at least way back in, centuries ago when I took biology and biochemistry. That was what they did in my textbooks, and I don't see any reason for them to have changed that. And they're 100% right, by the way. Those are high energy bonds, and they will react with a water molecule in such a way as to release a proton. By the way, this is another thing that we can thank the biochemists and biochemists for. And actually, it may shock you when I say this, I'm actually a big fan of this type of not nomenclature, but of this type of drawing over here that shows water's coming in and H plus is getting spat out. So that's what this type of thing is meant to show. Sometimes you'll see just the arrow coming in, meaning that there's some kind of addition reaction, and you'll see the addition products. Other times you won't see anything coming in, and you'll just see small inorganic pieces being popped out here. And that's going to represent some kind of elimination reaction, isn't it? It means that something's breaking up into multiple pieces, and maybe we're less interested in these small inorganic ones, and we're mainly interested in the pieces that are over here. But in the end, you will wind up with the inorganic phosphate. This would, in your biology class, this would be written as PI. In your Gen Chem class, this would be written as HPO4 2-, or in other words, the monohydrogen phosphate ion. The other piece is now adenosine diphosphate, which certainly we have other roles for in living systems. And we will also win roughly 30 kilojoules per mole. I don't really care that you memorize that number, not to mention that I realized this in the previous class. I'm sort of surprised no one has brought this up to me in previous classes, but I think, shouldn't that really say minus 30 kilojoules per mole, right? Because this is an exergonic process. We get energy out in the form of heat. I suppose it depends on your perspective, whether you're saying 30 kilojoules per mole is about the amount of energy that we gain, or whether we show that explicitly with a minus sign. I suppose you could make the argument either way. But this is certainly an exergonic process, one that for each mole of these high energy phosphorus oxygen bonds that we hydrolyze, we can expect to get round and about 30 kilojoules of energy each time. But what I want to point out here, and this will give you some idea of what to focus on and how to think about this chapter. What I want to point out next, and I'm going to do my very best to convince you of it, is this is not happening in a vacuum. This did not come out of nowhere. We've seen high energy hydrolysis reactions like this. For example, we know that acid anhydrides of this type are also high energy molecules. And just as the phosphorus oxygen bond here can be thought of as a high energy bond, so also these carbon oxygen bonds can be thought of as high energy bonds. And just as when we bring in a water molecule with loss of a proton, we get hydrolysis of this phosphorus oxygen bond plus 30 kilojoules per mole. We also know from chapter 21, you'll notice that in the class notes, I try my best to point back to chapters that you can review if you've forgotten some of these details, or maybe it's written a little bit differently than we were used to back then, but it's the same idea. In any case, we can certainly hydrolyze this acid anhydride and get 2 carboxylic acid molecules, essentially, out of it at the end. And just as C double bond O attached to an O is a high energy bond, so P double bond O attached to an O is a high energy bond. So I'm hoping that you can see that these two ideas are really the same thing. They aren't unrelated ideas. It's the same type of thing, only in one case we involve phosphorus in living systems, and we involve carbon in possibly a non-living system. So my point being is, it's not at all surprising that this reaction gives off energy to the tune of 30 kilojoules per mole. I didn't write down the energy change here. I suppose it depends to some degree on R. I don't think the energy you gain will be quite as high. I think it will be more in the 20 kilojoules per mole area. Check me on that, since I don't have that number memorized, and I certainly don't expect you to memorize it either. But I think you'll find when you look it up and are open-minded and fair about it, you'll say, oh, this is also an exergonic process. Maybe not quite as exergonic as this one, but still also exergonic. And if you can focus on the right pieces of the molecule, I think you'll see that it's no wonder that, that this process is one of the main ones by which we get biochemical energy. And again, where this is going to be helpful for your learning and for your grades later on down the road is to be able to make these comparisons. Don't shy away from making these comparisons. And don't shy away from understanding what's going on here. It's not simply memorizing this that's going to help you down the road. Yes, you are going to do some memorization for sure. There's memorization, by the way, in every subject. I might have told you guys this, but I was a double major when I was in college. I majored in chemistry and music. And let me, believe you me, there was plenty of rote memorization from my music degree as well. We had exams where the teacher, the professor would start playing a piece in the middle, and we'd have to say, oh yes, that's Beethoven's such and such piano concerto number whatever, movement 2. You know, so there's memorization in every field. Organic chemistry is no different in that regard. But if you can make these comparisons, and I feel like students are trying their best to avoid making these analogies, making these comparisons. Don't avoid it. It's well worth the little amount of work that it will take to put into that. It's going to save you so much trouble later on and make it that much easier to learn things. Good, so much for hydrolyzing ATP. I also want to look at the breakdown of fatty acids. First of all, in the form that we're used to seeing them in triglycerides or triacylglycerol. And then we'll also look at the breakdown of the fatty acids themselves. And then also, then we'll probably stop to take a break to do our reef pulling questions. And then we'll finish up with fatty acid biosynthesis. Again, my goal in all of this is going to be, we've seen reactions like all of these before. These are not new reactions for us. They're familiar friends. They're just in a slightly different context from what we might be used to. And as always, feel free to post questions in chat or to unmute yourself and interrupt me. I'll also be letting you know of some of the questions that people in the first section asked, since I'm betting a lot of you are wondering the same thing. But in chapter 27, we learned that triglycerides are one of the main ways that fats are stored in living systems, and certainly one of the main ways they're mobilized as well. We already know that first of all, this triglyceride is going to be a triester involving glycerol. Glycerol is 1,2,3-propane triol, and involving 3 fatty acid residues. So those R groups can be any of a variety of different groups, either saturated or unsaturated. And we already know that esters can be hydrolyzed. We learned that in chapter 21, and we went over that mechanism. So indeed, these esters in the triglyceride or triacylglycerol can be hydrolyzed. The mechanism is exactly the same as what we learned back in chapter 21. It's not a different reaction. It's the exact same reaction. Mechanism is identical. And in the end, you will get 3 fatty acid residues, or more likely 3 carboxylate ions, since if we're at biological pH around pH 7, we're well above the pKa of these carboxylic acid groups, so they're likely going to be deprotonated. And we will also get a molecule of glycerol. And you can see the way I drew it here, I was trying to be kind of cute and draw it using a Fisher projection, even though there's no chiral carbons here, right? Dihydroxyacetone is not a chiral molecule. We'll get to the fate of these fatty acids in a moment when we get to beta oxidation of fatty acids. But what about the glycerol? The glycerol is also a molecule that our bodies know what to do with. First thing we're going to do is phosphorylate one of those OHs. And now I'm actually not being cute at all by drawing in a Fisher projection, because now it matters which of those 2 OH groups we put the phosphate on. It turns out it's going to be the one on the bottom. And then in a step after that, we're going to do an oxidation reaction. We're going to use NAD as our oxidizing agent, NAD plus, I should say. And I think what you'll find in general, I won't say without exception, but I think what you'll find in general, even as you go on into your biochem classes, is NAD plus and NADP plus act kind of like chromium trioxide, or maybe like desmartin periodinane, or maybe like pyridinium chlorochromate. So we discussed those oxidizing agents back in chapter 17. And if you've forgotten about those, I've given you here, I've tried to give you always in these class notes, which sections of your textbook to go back and review, so you can refresh your memory on those. And this is going to do nothing other than oxidize this secondary alcohol to a ketone. So of course, now there's no chiral carbons here. These are both CH2s, and that carbon is now sp2 hybridized. So that's nothing other than dihydroxyacetone phosphate. That's an intermediate that our bodies well know what to do with. We have pathways in place to deal with that molecule. It's used as an intermediate in a variety of contexts. And so the point being, starting with a triglyceride, we can break it down into 3 fatty acid residues as carboxylate ions, and also by an NAD plus oxidation, go from glycerol to glyceraldehyde 3-phosphate to dihydroxyacetone phosphate. So these are all reactions that we understand. I don't think there's any reaction that you see here that you can make the argument we've never seen anything like that before. You can try, but I don't think I'm going to believe you. We've seen all of these reactions before in one form or another. So we've got our dihydroxyacetone phosphate. That's great. We've also got 3 of these fatty acid molecules. What are we going to do with those? How do we get the energy out of the fatty acids? And by the way, I think you'll see the form that these class notes took. I started very much on a high spiritual level here, and I was very, very well behaved, and I put all these things into my class notes with color codings, and I intended to carry that out further. And then I eventually just gave up and used the things that are in your book because I realized I could not do any better than what was in your book. So we'll save that for next time when we get to some of these more complicated pathways. But while we're on the topic of fatty acid breakdown, what happens to those long chain carboxylate ions? Well, one of the things that happens to them is they get transferred to an acetyl coenzyme A molecule, and that, transferred to a coenzyme A molecule, and that's what I'm here representing here is S-CoA. So these now are going to be in the form of thioesters, and we have enzymes that can do that for us, that can transfer the acyl group onto a coenzyme A molecule. And coenzyme A is a thing, by the way. It's a medium-sized molecule, I would say, by biochemical standards. I sure don't expect you to memorize the structure of coenzyme A, but it's there for your perusal. You can look it up if you want to. It's well known. But these now are thioesters, not just regular carboxylate esters. And we have mentioned thioesters at least twice that I can think of in your textbook. I might be missing 1 or 2 of them. One time way back in chapter 2, when we learned functional groups in the first place, we mentioned thioesters, and then did not see them since until now, here in chapter 29. So I think that's largely why they introduced them. We also mentioned thioesters, I believe, again, double check me on this, but I believe back in chapter 21, when we were talking about the order of reactivity of the different acyl derivatives. And we placed thioesters as being somewhere in between regular carboxylate esters, where this sulfur is an oxygen, and anhydrides. So they're more reactive than anhydrides, and they're less reactive than anhydrides, and more so than regular carboxylate esters. Do you need to know what the S-CoA? Yes, you need to know it's coenzyme A. Do you need to know the structure? I just said you don't need to memorize the structure of coenzyme A. But certainly you need to know what that is. I don't just want you thinking of it as an S, a C, an O, and an A. You need to know that's a coenzyme A molecule. And so that's one way. You'll learn there's other ways that esters are carried as thioesters when we get especially to the opposite pathway of this, which is fatty acid biosynthesis. So we'll look at both of those. But in any case, the first reaction in the sequence involves the flavin-adenine dinucleotide. And I think what you will find, just as we said that NAD plus and NADP plus act kind of like a chromium oxidizing agent, FAD usually reacts like the opposite of catalytic hydrogenation. Or we could flip those ideas in their head. We could say that NADH and NADPH act usually like sodium borohydride or lithium aluminum hydride in terms of their reactivity. Obviously, we don't have lithium aluminum hydride coursing around in our body. There's no possible way it can't coexist with water. You just get a big fire. Likewise, FADH2, I think if you're fair about it and open-minded, you will find going forward that it behaves something like catalytic hydrogenation. FAD is like the opposite of catalytic hydrogenation, and FADH2, something like catalytic hydrogenation. There are exceptions. In fact, I think we'll run into one exception already today, but I think you'll find it's most common that those will be the case. Anyway, when we do the opposite of catalytic hydrogenation to this molecule, we will introduce a carbon-carbon double bond conjugated to the carbonyl that's in the thioester with coenzyme A. And that's by using, of course, an enzyme with FAD as our cofactor, the flavin-adenine dinucleotide. And once we have that in place, we can do what amounts to nothing other than a conjugate addition of water. We talked about that back in chapter 23. We said that water was one of the nucleophiles that, given a choice, would rather add to the beta carbon of an alpha-beta unsaturated carbonyl compound. And this is no exception. So this is an addition reaction. We're going to hydrate this double bond, and you will get this beta hydroxy ester over here. And we've seen reactions like that before. After that, the hydroxy group gets oxidized from a secondary alcohol to a ketone. We would use desmartin periodinane or something like that in silico, I think is what they say, right? In glass as opposed to in vitro, that'd be in a petri dish, or in vivo, which is in living systems. So this is neither in vitro nor in vivo. This would be in silico. I think they also use that to mean done by computers. So be that as it may. In living systems, we would expect to use NAD+, or in this case, it's NAD+. Sometimes we find it's NADP+. These are substitutes for the chromium-based oxidizing agents, which we went over largely in chapter 17, but we covered that in subsequent chapters as well. And so we see our secondary alcohol is oxidized to a ketone. By the way, I should mention, although I don't care if you memorize the stereochemistry, of course, in living systems, with this addition of water back here, we would get only one stereoisomer, right? Not that it matters, because that stereochemistry is going to get immediately wiped out, and we'll go from the secondary alcohol to a ketone, and that carbon's no longer chiral. So that's very common in living systems, that you will set up just one stereoisomer, that then in almost the next breath, that stereocenter gets wiped out and converted to an achiral carbon, such as by going up to sp2 hybridization. So that's real common. At that point, we introduce another acetyl coenzyme A molecule, and we will we will introduce another coenzyme A molecule, and we'll give off a molecule of acetyl coenzyme A. That will correspond to the red part of this molecule. And as I pointed out in the class notes, this reaction is nothing other than the opposite of a Claisen condensation reaction. In a Claisen condensation reaction, one could imagine this thioester and this thioester reacting with loss of coenzyme A to give this beta ketoester. So the mechanism is exactly the same as what we've learned. It's just the Claisen condensation, but exactly backwards, happening in reverse. So this is not a new reaction for us, and that's going to help you a lot when you get onto biochemistry. You won't just be relying on memorization. This is going to be a reaction that you understand. And if you needed to, you could imagine drawing out the mechanism. Of course, in real life, this will all be mediated by enzymes, which will speed up the reaction many, many orders of magnitude. But conceptually, this reaction is nothing other than what we've already talked about. It's simply a Claisen condensation, which we just talked about in chapter 23, except it's done in reverse. And so that's basically it for fatty acid breakdown. All we've done is we've cut out 2 of the carbons in the fatty acid, and we now have a fatty acid that's 2 carbons shorter. This now goes back into the beginning of our sequence here. If we're looking at fatty acids of plant origin, we're occasionally going to run into carbon-carbon double bonds that will already be present. Of course, they will be cis double bonds rather than trans, because trans fats are not naturally occurring molecules. So I think in some cases you'll get promoted one step. You won't have to use the FAD to introduce the carbon-carbon double bond because you'll already have that there. But then you'll add the water, which will give the hydroxy compound, and then oxidation with NAD+ to give the beta ketoester. And in any case, whether saturated or unsaturated, this keeps going around and around and around and around until nothing's left but acetyl coenzyme A molecules. And those, again, are important biological intermediates that we have well-established pathways to deal with the acetyl groups that are in acetyl coenzyme A molecules. Good. Any other questions so far? My plan now is going to be to take a little break and do our clicker questions, and then we'll come back and finish with fatty acid biosynthesis. Or you can be thinking of if there are any questions that you might have. First of all, so my first question for you guys is mostly a review from even Gen Chem as well as earlier in organic chemistry. And we'll give you an idea of what to focus on in this chapter. This is not only what to focus on, but it'll give you an idea. And the question is, which of those 4 reactions is an elimination reaction? And I would put it to you that one of those 4 is an elimination and the other 3 ain't. Please do not put E. E is not the right answer here. But one of those 4 is going to be an elimination reaction. All right, well, I would expect you to be able to analyze all of these, that you would say that the last reaction here is nothing more than an isomerization reaction. So that's not an elimination. Here, this phosphorylation reaction is not an elimination. It's, if anything, a substitution reaction. You've got the hydrogen and the phosphate switching places. So that's got to be some kind of substitution. Over here, you've got an OH group being oxidized to a ketone, going from a secondary alcohol to a ketone. That's not an elimination. This one is an elimination. And we're losing the elements of water. We're losing H and OH to give a carbon-carbon double bond. And by the way, you will notice that I automatically went from drawing this carboxylic acid group in a wedge bond to drawing it on a straight line. And that's something that I will expect will be automatic at this point, that you're analyzing the structures you're drawing and you're understanding the consequences. You're not going, ooh, I'd better make that a wedge bond just to play it safe. No, that's not safe. It's the opposite of safe, in fact, because when we go to sp2 hybridized carbons, that whole region of the molecule now is flat, right? sp2 is trigonal planar. So we lose dot and wedge bonds over there. So I'm hoping that by now that sort of thinking is automatic. In any case, I think the best answer is A. Let's see what you guys thought. Yep, rather overwhelmingly so. Good. So next question, and my final for the day, which of the following is a redox reaction? And again, of those 4, 3 of them are neither oxidation nor reduction, and 1 of them does involve redox. So your goal is to figure out which one involves redox. So let's see, of course, a simple isomerization is not redox. This is a substitution reaction, that's not redox. This also a substitution reaction, you're just hydrolyzing the acetate ester. That's just the acetate, the acetyl and the hydrogen switch places, that's not redox. Here we do have redox. We've got a secondary alcohol going to a ketone. So that's an oxidation process. And I think if you wanted to convince yourselves, if you went in there and you found the oxidation number of the carbon atom in question, don't quote me on this, but I believe that if you went and did that, you'd figure out that the oxidation number went from -2 to 0 for that carbon atom. So that's an oxidation that's occurring, which falls under redox. So I think C is the best answer. As did you. Good, so the remaining points are, oh, and the remaining points are free for attendance. Oh, let's not forget, we'll have a very special guest, not this coming Friday, but the Friday after that is reading day. And on reading day of finals week, I would always traditionally have Bella Day. We haven't been able to do that for the past 2 semesters. This is an older picture of her. Actually, I recognize it being in my house in Minnesota, so that was before I moved down here. That picture's got to be about 10 years old. She's kind of gotten grayer, just like a person as she's getting older. So everything's getting gray, but poor old Bella. But this is back when she had teeth, but her personality has never changed. It's always been exactly the same, always kind of like a dog, always dumb as a rock and loves everybody. So she enjoys it. I wish I could also bring Barnaby, but he would not enjoy himself at all. He would probably try to hide under, behind, whatever he possibly could, and he certainly would never come out to get attention. It's a shame, but he really only trusts me. Bella's fine though. She loves everybody. She's not afraid of anyone. So if you're not allergic, please don't come if you are allergic. But if you're not allergic to cats, you're welcome to come meet Bella. And I'm sure I'll remind you again, that's not this coming Friday, but the one after that. And she loves getting attention from as many people as possible. Okay, so I think that's all we need to say about that. We still have about 5 minutes to cover fatty acid biosynthesis. I just want to, on this one, let's see if it let me. The answers, I think, were A followed by C, so we'll make sure that gets saved for when I eventually upload that to eCampus. Good, so let me move all these things around so we can read from our class notes. Good, so what about the reverse process? We've seen how we get energy out of fatty acid breakdown. What about storing energy in fatty acid biosynthesis? This one's a little bit more fiddly because there's a lot of transesterification or trans-thioesterification reactions. And I'm not familiar with functionally why we do this. There's always reasons for all of these that have to do with the logic of the pathway. But in the end, I think you'll see that it basically does the exact opposite of what we just said. We're going to take together 2 carbon pieces as acetyl coenzyme A molecules, and one by one stitch them together to make a chain as long as we need it to be. The first step involves using CO2 as an electrophile, and we've seen that before. We talked about carbonation of Grignard and alkylithium reagents back in chapter 18? No, that's ethers. That might also have been in the first semester. Boy, it's a blur for me. But I left all of the necessary addresses, so to speak, in your class notes. But why do I say CO2? Well, because CO2 and the bicarbonate ion and carbonic acid and water, all of those are in a mobile equilibrium at all times. And where in the body is that equilibrium taking place? Well, it's in our lungs, of course. That's where all of that's taking place. So carbon dioxide can act as a as an electrophile, and one can imagine it's as if the methyl group on acetyl coenzyme A were getting deprotonated, and indeed we can lose that proton by forming the enol, and that's nothing other than a chapter 23 type reaction. That enol will then add to CO2, and you'll get a molecule that looks like this. So this is now, now we've just added essentially a carboxylate group, beta to the carbonyl group. And this can now, this is going to undergo the first of 2 or 3 transesterifications. This is nothing other than a substitution reaction. We need, for some reason, which again, it's not my field, and I don't care, I don't think you need to focus on this in our class either, but for some reason, we need to get our growing chain off of coenzyme A and onto something called acyl carrier protein, ACP. And that's all that's happened here. We've released coenzyme A and introduced this acyl carrier protein. Then we get another acetyl group brought in, attached to yet a third thing, which here I've just given up and called it R. So this is another acyl carrier group. Doesn't really matter because we're about to lose that carrier group over here as this thiol, plus a carbon dioxide molecule. And again, losing carbon dioxide is going to be very favorable energetically. That can now bubble out of solution, so to speak, and drive the reaction forward. And we get this sort of beta keto thioester type structure over here. This now can undergo reduction. Here we're using NADPH as a reducing agent. That's going to do the same thing that sodium borohydride would do. In fact, if we took this and treated it with sodium borohydride, we would expect to get this beta hydroxy thioester. Of course, in living systems, you're going to get just one stereoisomer over here. Not that it matters, because we're about to lose water and wipe out the stereochemistry that we just went to all the trouble to put in to get a carbon-carbon double bond. So there's your dehydration reaction. This can now undergo another reduction, and will reduce the carbon-carbon double bond to a carbon-carbon single bond. This is kind of like catalytic hydrogenation. And I'll just say, this is always something that rings off alarms in the dark recesses of my mind. I would have expected FADH2 to be the reducing agent here, but it's not. It's NADPH and H+. I don't care if you guys memorize that for our class. That's not important for our purposes. For biochem, though, they will be very interested in your memorizing these things, probably, at least if my memory holds. So you might want to stick in the back of your mind, or in your mind put a little bright red sticky note over here saying, watch out, this one's a little weird, looks like it ought to be FADH2, but it's NADPH and H+. Either way, we've now gone from a 4-carbon group, or rather a 2-carbon group, to a 4-carbon group on our acyl carrier protein. This then comes back in, and we go through that as many times as necessary in order to build up our fatty acid chain. With that, I'm out of time, so I kind of need to stop that for today. I'm very pleased with myself that I made it through both lectures without nearly falling asleep. Be that as it may, that's not your problem, but I think we're working that one out. So other than that, have a great day. I will see you guys on Friday. Again, it's not this coming Friday that's Bella Day. It's the one after that. But I hope, at least if you're not allergic, that you'll get to meet Bella. If you are allergic, please don't come, or at the very least, take a bunch of antihistamines, because we don't want you suffering. So have a great day. We'll see you on Friday.